All right, everyone. We're going to start a problem today. It's another problem with a loop rule, Kirchhoff's loop rule and Kirchhoff's junction rule. And in this case, I'm going to solve it actually this exact same way I did last time as far as solving the system of equations go. But it's a little more complicated. I've got some internal resistances for batteries. That's the two 1 ohms that you see up there. But basically what you see is a battery, a 90-volt battery attached, of course, having an internal resistance of 1 ohm, driving a current of I1 that then goes around corner A. I've labeled these so we can explain to you what loop I follow. Then goes through a resistor of 20 ohms, and then it goes through corner E, where there's a junction that breaks off into two other currents. So at junction E, if I want to go up, I'll go to the negative terminal of a 45-volt battery that then runs into a 1 ohm internal resistance, and then that drives a current I2, and that runs through a 40 ohm resistance. Or if I went the other way, I'm assuming I'm going the direction of I3 again. Notice I've labeled the direction of I3 up here. And that's just going to be some current that I think is going to go through a 30 ohm resistor. So we're going to solve the system of equations, or excuse me, this circuit for the currents. And then I'm going to explain to you how to actually determine the terminal voltage of the individual batteries. I've done it a little differently. I'm not actually working it out in real time. I've already worked it out. I'm just going to slowly show you the parts because I'm going to reuse the same problem to show you another method called the Nodal Method, which I find is super, super easy. So let's check this out. So first off, I'm going to consider the loop CBAEDC. So CBAEDC. So I'm going around that loop that way. Notice that happens, and this node happens to be the current I1. It's in the same direction. And then through this node, it's also the same direction as I2. So resistances will actually be voltage drops. So starting at C, I run into the negative terminal of a battery, and then that goes into the positive terminal. So I know the difference has to be an increase in 90 volts. And so I went from negative to positive, so it's plus 90 volts. I called that current I1, so it'll be Ohm's law, V equals IR, would be 1 ohm times I1. Now I'm going to basically assume all these things have 3 sig figs. Basically 1 decimal place for the 90 volt, 2 decimal places for the 1 ohm, 1 decimal place for the 20 ohm, so on and so forth. And later I'll even drop the ohms and volts just to make the math easier. So again, C plus 90 volts minus I1 times 1 ohm, or 1 ohm times I1, minus 20 ohms times I1. Now I'm up to here. And now I go from the negative side to the positive side of a 45-volt battery. So that's a plus 45-volt change. And then I'm going the direction of current. So it's minus minus 1 ohm times I2, minus 40 ohms times I2. And that gives me, since I'm back where I started from, a sum equal to 0. So I can combine like terms, and I get what I now call equation 1. So with equation 1, it's basically the same as the other one, just I combined the like terms, making this minus 1, minus 20, so that'd be minus 21, and making this minus 1 and minus 40, making that minus 41. Now I'm going to go through a different loop. This loop is going to be EDCFGE. So EDCFGE. So this time I'm going around the loop in this direction, and I'm starting here. Notice on this node, I am going the same direction of the current. So again, the resistances will be a voltage drop, but this one I'm going against the direction. So the resistances will actually cause a voltage increase. So first off, I go from the negative to the positive terminal of a 45-volt battery. So that's a voltage increase of 45. So I'll put plus since it's an increase. Minus 1 ohm times I2, minus 40 ohms times I2. And then I finally get to this resistor, and I'm going in the opposite direction of current, so it must be a plus, or a voltage increase of 30 ohms times I3, but I'm now back where I started from, so that's equal to 0. Again, combining like terms, and I get a sort of simpler version of equation 2. 45 volts minus 41 ohms times I2 plus 30 ohms times I3. So I think y'all can all see where the combining like terms changed equation, the top equation into equation 1 and that third equation into equation 2. All right. So we've got three unknowns, I1, I2, and I3. We've only got two equations. Of course, the third equation comes from the junction rule. I could use the junction at E. For instance, I could realize that I1 comes into E, I2 and I3 leave E. So I'd say I1 is equal to I2 plus I3, or I could do like I did do. I consider junction C, in which case I've got I2 and I3 coming in and leading to I1. So I'd write I3 plus I2 equals I1. So I2 plus I3 equals I1 is what we went with. We no longer have to refer to that circuit anymore until we get to the very end and we want to try to look at what those currents were and maybe determine some terminal voltages of the batteries. So now I have equation 3, I2 plus I3 is equal to I1. When I make my loops and I force one loop to go through this node and then I force the other loop to go through this node as well, that forces me to automatically have a common I2 in both of the equations, 1 and 2. The advantage of that is I can always then take the junction rule, solve it for that one current they have in common, and then replace the currents that they have in common, the current itself that they have in common, with what you get when you solve this for that common current. So in this case, I2 would be equal to I1 minus I3. So that's actually what we're going to do. So you notice I solve equation 3 for I2 and plug I2 as a function of I1 and I3, that's what those parentheses mean, into 1 and 2. So I'm just going to plug I2 equals I1 minus I3. I'm going to plug that into equation 1, and then I'm going to plug it into equation 2, and that sort of thing. So equation 3 prime is basically when you solve equation 3 for I2, you get, like I said, I1 minus I3. Now I plug 3 prime into 1. Notice I get 135 minus 21 I1. And here's where the different part comes in, minus 41 times not I2, but I1 minus I3. And then that's all equal to 0. Again, I can combine like terms. So distributing the minus 41 through here, I get minus 41 I1, and then I get plus 41 I3. So the minus 21 and the minus 41 gives me minus 62. So I now have what I'm calling equation 4, 135 minus 62 I1 plus 41 I3 equals 0. So that's with it combined terms and everything like that. Now that really is just equivalent to equation 1, except getting rid of I2. Generally speaking, when I go back and plug, if I solve and actually get a current for I1, for instance, and I want to find I3, I really should go back to one of these and solve it. But this time, for some odd reason, I ended up plugging the result in I4. So just keep in mind that that's not the best way. You want to try to keep the least manipulated equation. You want to use that to substitute stuff into, just in case you made any arithmetic errors. It's less likely that using one of these equations is going to give you a problem. Whereas this one, since you've done so much stuff to it, it's more likely to be wrong. So anyways, I'm still doing it in this one. That's not the best of practice, but just be advised. All right, so that's equation 4. Now I'm going to plug 3 prime. Remember, that's just I2 equals I1 minus I3 into equation 2, which is the 45 minus 41 I2 plus 30 I3. I made a writing error there, but I just crossed it out and put a 41. So it's supposed to be 45 volts, which I just call 45, minus 41 times I2, but I wrote 45 because I'm a crackhead. But anyways, not really a crackhead, I'm just being funny. So I replace I2 with I1 minus I3, close the parentheses, and then plus 30 I3, which is what we had there. Again, notice I'm just willy-nilly dropping the sig figs, dropping the units. We're just doing math right now. We're trying to make sure we don't make any boo-boos. We can always recover those units and stuff later, and I will point that out as we go. So combining like terms in that, I took a few more steps than I normally do. One, because I wrote the 45 wrong, or excuse me, the 41 wrong. It looks like I did again. So let me go ahead and make that correction on the fly, which means a lot of my answers are going to be jacked up. This is so aggravating. So this becomes 41I3. Okay, so now I say 45 minus 41I1. Now 41 plus 30 is not 75. It is in fact 71. So yay, that's going to follow us through the rest of the problem. Another boo-boo, even though I worked it out in advance. Just awesome. Just awesome. All right, anyways. So what I'm going to do now is try to combine these two equations. The problem is, when you want to combine equations, you might want to add them or subtract one from the other, or maybe even sometimes, especially when you're dealing with trig functions, sometimes you want to divide one by the other. In this case, I want to add them and get one of the variables to just disappear. Well, here I have a 62I1 and here I have a 41I1. So it'd be really, really wonderful if I had a plus 62I1 here instead of a minus 41. So guess what? I'm going to multiply it by negative 62/41. That's crazy, I know, but this is the age of calculators, so we can do that really easily. Easy peasy, except for this typo that I got to keep, or this right O that I got to keep replacing. So I'm going to take 5 and I'm going to multiply it by negative 62/41. So negative 62/41 times 45 is the first term. Negative 62/41 times negative 41, I1 is the second term. And then negative 62/41 times 75, which is actually supposed to be 71, is the last term. So I'm going to have to do some calculator work to repair that screw up, but we'll work on it. It's not a big deal. So this becomes, notice the first equation, 4 hasn't been manipulated at all. It's just 135 minus 62I1 plus 41I3. When you multiply negative 62/41 by 45, you end up getting, notice 62 is a little bit bigger than 41, so clearly it's going to make something bigger than 45, except for the negative. So I get negative 68.05. I'm carrying one extra digit because remember I said we were pretending it's 3 sig figs everywhere. Minus 60 or plus 62 I1, that was the whole purpose of multiplying by negative 62/41. It would make this positive and it would change the 41 to 62, so that worked out perfectly. Where we have a screw up here is this 113.4, which isn't the right number at all. That's actually supposed to be, let's check. Let's see, 62 times 71 divided by 41 gives me 107.3 or 0.4. So that's a boo-boo we're going to have to continue dealing with through the rest of this problem, but that's not horrible. We can figure all this out. Okay, so now I'm going to go to actually adding these two. Notice what happens is exactly what we expect. I'll do 135 minus 68.05. Again, using my calculator or carrying one extra digit, I got 66.95. In some sense, I'm actually not carrying one extra digit. I'm actually carrying like 2 extra digits because when you add, the sig fig rules are different. But either way, I'm just keeping 4 sig figs because I'm pretending like everything's 3. Of course, the negative 62 plus 62 gave me the 0 I1, which is what we were shooting for. And then the 41 minus 107.4 gives me not negative 72.4, but negative 66.37 ohms times I3. So you should be keeping up with this with your own calculator. Remember, this video, you can just pause it at any time. Just make sure you can verify the numbers I come up with. So now, if I pull this term over here, it'll become positive, and this one will stay positive. So this is no longer 72.4, but 66.37. So it's 66.37, which doesn't give this, and it doesn't more than likely give that. So let's do 66.95 divided by 66.37. I'm going to get 1.0 1.01 amps. 1.009 actually. So it gives me 1.009 amps, which I'm going to call 1.01 amps is equal to I3. So forget about that number, forget about this number, that's the new correct number. Now that I have I3, here's where I made a little boo-boo. I should have put this back into equation 1 or 2 because those are my least adulterated equations. For instance, if I put it in I2, then I could immediately, or excuse me, equation 2 up here, I would have I3 and I could solve for I2. But instead, I looked up and didn't look far enough up and just went to equation 4. And that's fine. Like I said, I don't think I made any other errors, but I might have. We'll find out. So I'm going to plug this 6, which is the equation for I3, or the actual current I3, into equation 4. I get 135 minus 62 I1 plus 41 times not 0.9247, but 1.009 amps. Okay, so basically what's going to happen is 135 is going to be added to 41 times 1.009 amps, and the 62 will come over there. So I'll end up getting 135 plus 41 times 1.009. That's 176.369, or I'll call it 176.4. So I'm basically going to divide 176.4 by 62. So dividing 176.4 by 62 gives me I1 is equal to 176.4 volts over 62 ohms, which gives me 2.845, so 2.845 amps is I1, which I'm going to call I1, of course. Of course, I1, I'm going to call that 2.85 amps. And that's going to be what we call equation 7. So again, this number is not right, but that one is correct. Sorry about these errors. Now that I've got I1 and I3, I can just go back to the junction equation and find out what I2 is. So actually, just yeah, solve for I2. Now the good news is I've already done that. And basically you could just say, looking back up here, I2 is just I1 minus I3. So really all I have to do is take I1 minus I3, which would be 2.845 minus 1.009, and I'll get 1.836, which is pretty close to my final answer anyways. So I2 is just equal to I1 minus I3, just gives me 2.845 minus 1.009 amps, which is in fact 1.836 amps, which I'm going to say I3, or excuse me, I2 is equal to 1.84. So yeah, I did make that mistake early on, and that made it a little more complicated, but basically the algebra and arithmetics are all the same. Now the beauty of this is I finally got an answer. I'm going to write down this answer up here just to keep track of it. So it turns out I1 is equal to 2.85 amps I2 is equal to 1.84 amps. By the way, these are big currents. Wires don't generally like carrying 1 amp or higher. Everyday wires, anyways, the stuff like you put inside of devices, or trying to use a small, but the big ones that plug into the wall are a little bigger. They can handle more. But a whole amp's a lot of current. So I3 finally is 1.01 amps. So that's what my answer should be. Now, the beauty of that is I can now explain to you how to calculate the terminal voltage for each of these batteries. So notice if I go from here to here, it's a 90 volt drop, increase. Sorry, you're not looking at that at all. If I go from here to here, it's a 90 volt increase. It goes from, say, 0 or maybe 5 volts to 95 volts, or from 0 to 90. But then once I go across here, this is the actual terminal of the battery. So that drops by an amount, I1 times 1 ohm. Well, I1 was 2.85. So if I multiply that by 1, I get 2.85. So this is going to be almost 3 volts shy of 90. So it's going to be having a terminal voltage roughly of 87. Okay, 87.15. So that's the way you can find the terminal voltage for this battery. Similarly, if you want to find the terminal voltage for this battery, notice it jumps from 0 to 45, or from some value to 45 higher. Again, we don't necessarily know what that voltage is. But then across the 1 ohm resistor, which is the internal resistance, we get to the other terminal. So again, it's going to be 45 volts minus this 1 ohm times I2. Well, in this case, I2 is 1.84 amps. So if I multiply that by 1, it's going to be 1.84. So basically, this 45 volts is going to have a terminal voltage of almost 2 volts lower than 45. So it'll be 43.16, or 43.16 volts. So that's how you actually find the terminal voltage as well. So I've now shown you an example of using Kirchoff's loop rule, junction rule, and how to solve a system of equations. I reminded you, of course, that if you take 2 loops that have a common current in it, like doing this loop and this loop, both equations will have I2 in it. That allows you to eliminate I2 using the junction rule, and making it only in terms of I1 and I3. So that's always a way that you can solve the system of equations, at least the simpler ones where they're just like 2 loops. If you were to take the big outer loop, that would be acceptable as well. But notice that one's going to have an I1 and an I3, but no I2. And this one's going to have an I1 and an I2. So it's a little bit different technique that you come up with. I hope that helps.